Let's start by remembering what we know about continuity. So if we have a function let's call it, for creativity's sake, f. And let's say that f has a hole at some number c. So we would say that f of c is the y value for the x value c. Then if we look at the limit as we approach, let's get a different color. There we go. If we approach x values towards c from the left side of c, that means we want to look at corresponding f of x values with these same x values. I can see that the limit as x approaches c from the left of f of x equals f of c. And similarly, the limit, look at the other side, values of x approaching c from above or from the right have corresponding f of x values that also approach f of c. So we would say that the limit as x approaches c from above or from the right of f of x equals f of c. And as we learned in the previous lesson, that means that, so therefore, let's use a different color. Therefore, the limit as x approaches c exists, and the limit as x approaches c without a plus or a minus of f of x equals f of c. So here the limit exists even though there's a hole in the function f at c. Is the function continuous if there's a hole? Well, clearly the answer is no, but the reason is that f of c, the value that you get if you plug c into the function, well, here f of c doesn't even exist. It could exist and be up here. As long as f of c isn't the same as the value of the limit from the left and the right, then the function is not continuous. So let's think of it positively. In order for the limit to exist, we need to approach the same y value from the left or right. In order to have continuity, we need to not only approach the same value from the left or right, but that value needs to be defined and it needs to be right there at the same value. And now we want to look at something more. In order for a function to be differentiable at a point, it must be continuous at that point, and it can have no corners. That does not look clear. Let's see. No corners. No cusps. I'll draw a cusp in a second. And smooth is one of the ways that we say that it has no corners. So let's look at these words. Let's see if we can make sense of these words. So here's a function. Let's call it g of x. And here is our value c. This function g of x is definitely continuous at c because we're approaching the same value from the left to the right, and the value right at c is also that same number. However, just like the average rate of change, and certainly exactly like the instantaneous rate of change, we're looking at a slope. Well, let's see what happens. Let's look at the slope at two places. Let's look at the slope up here, and I'll call that B. If I draw a line, and that line was supposed to touch the graph smoothly, at this value B, f of B, is it possible to draw more than one line that smoothly touches the graph at BF of B and only touches at that one point? Exactly right. There's only one possible line that is tangent to the function g of x at b g of b. But now let's look at the second point. Here's a line that only touches g of x at one point, at c f of at c g of c. Wait a second. Here's another line, and that only touches g of x at cg of c. Wait. Here's another line that also only touches g of x at c g of c. In other words, if we have a corner, if we have a sharp turn, then we do not have a single tangent line with infinitely many tangent lines. So that is why we can have no corners. Well, let's look at cusp. What in that world could a cusp be? Okay, we're going to call this G. How about J of X? And let's say that this is our value of C. Right here at C, J of C, the tangent line is vertical. Well, the slope of a tangent line is undefined. And that means that we have an undefined derivative. Because the derivative is just the slope of the tangent line at a point. Well, if the slope of the tangent line is undefined, the derivative will be undefined. So again, it's just at a particular point here at Cj of C. So if our function has no corners and no cusps, and the way that we write it, not exactly rigorously, but more rigorously, is to say that f of x is smooth in a neighborhood about C, f of C. So neighborhood. Let's see what we can see with that. So there's C. This point is C, f of C, and a neighborhood about C, f of C is an open interval that includes C, f of C, and we get as close as we need to get to C, f of C, but we need to have some space around it. So like a little bubble around C, f of C, we need f of x to behave nicely or to be smooth in that open neighborhood. So if f of x has no corner at x equals c and there's no cusp, then we would say that f is differentiable at x equals c. The formula for the derivative is exactly the same as the formula for the instantaneous rate of change. I don't know if that's better or worse. Okay. We're going to be using this formula, but let's learn at least how to read these different notations. So when there's a strike here, it's f prime of x. We can also talk about the derivative as df dx, which we read df dx. And it is the limit as h goes to 0 of f of x plus h minus f of x all divided by h. In a moment, we're going to look at these first, the beginning rules for derivatives, because we can't do much with the definition without getting bogged down in some algebra. Although I promise you we'll get to do some algebra. All right.